Today, we're unraveling a modern mystery. We're going to look right under the hood of the artificial intelligence tools that are completely taking the world by storm. Our goal in this explainer? To discover the hidden, secret search engine that's actually operating inside nearly every enterprise AI out there. Okay, let's dive right into this, because honestly, this is the central paradox of modern AI. Imagine a lawyer asking an AI about a newly published law, or a doctor asking about a clinical trial that just came out yesterday, or, a software engineer asking about their company's private proprietary code. The AI can write a brilliant sonnet in the style of Shakespeare, but it completely fails to answer these seemingly basic questions. So what's going on? If it's already trained on the world's knowledge, why on earth can't it answer? Well, the answer lies in the huge gap between an AI's brain and real-time reality. See, a large language model, or LLM, has billions of parameters, but its knowledge is totally static. It is literally frozen in time at the exact moment its training ended. And on the flip side, we have all this missing information. Today's news, private company guidelines, dynamic data sets, the AI simply can't access what it has never seen.
Section 1. The AI memory problem, the amnesiac genius.
We're dealing with what you could call the amnesia genius problem. And before we get into the weeds of how we actually fix this memory gap, I want to offer a quick mental palate cleanser. We're going to be talking about a technique called Retrieval Augmented Generation, or RAG. And it's so important to understand that retrieval is not magic. It's not some mystical band-aid that just magically makes AI smarter. It's actually one of the most elegant engineering breakthroughs in modern computer science.
Let's break down exactly why these massive models forget, or really, why they can't just memorize everything forever. An LLM is stuck with static training cutoffs and static parameters. And the crazy thing is, when confronted with a gap in its knowledge, it doesn't usually just admit defeat. Instead, it often hallucinates, confidently making up factually incorrect stuff. Plus, no matter how massive a model gets, it inherently lacks access to your company's proprietary, behind-the-firewall enterprise data.
Section 2. Anatomy of a question. Journey through the pipeline. So, how exactly do we build a bridge between this brilliant but amnesiac language model and the ever-changing external world? Well, we take the AI on a highly structured journey, starting with what's called the naive RAG pipeline. When a user asks a question, we don't just blindly send it straight to the AI. Instead, the query goes through a retrieval phase where it searches a database of indexed documents for relevant chunks of information. Those chunks are then combined with the original query to form a supercharged prompt. This basically grounds the LLM in actual verifiable facts before it ever generates an answer.
Step by step, the journey looks a bit like this. First, the user query is submitted. Second, we generate an embedding, which is just a fancy way of saying we translate the text into a mathematical vector. Third, we run a semantic search to find information that matches the actual meaning of the question, rather than just doing a basic keyword match. And fourth, we assemble that retrieved information into a context window for the AI to read. So, instead of trying to store the whole world in its brain, the AI just learns to look things up precisely when it needs to.
Section 3. The hidden search engine. Engineering the perfect match.
Retrieving the right document from a massive database is incredibly complex. If we peek into the hidden engine room, we see that we actually rely on two fundamentally different ways of searching. Vector search looks for semantic meaning in high-dimensional space, so it understands the concepts. BM25 search, on the other hand, is your traditional keyword search. It looks for exact term precision. And the thing is, each has blind spots. Vector search might understand your intent perfectly, but totally miss a specific part number. Keyword search finds that exact part number, but completely misses the broader context. That is exactly why modern systems use hybrid search, which combines both.
But wait, how do you actually combine a vector similarity score of, say, 0.85 with a keyword score of 12.4? It's like mixing apples and oranges. As AI researcher Guillaume Laforge puts it, reciprocal rank fusion, or RRF, ignores the scores entirely and focuses on rank. By operating purely on the position of a document across multiple search lists, RRF perfectly merges those totally incompatible search scores to find the absolute most relevant data.
And this leads us to the industry-standard two-stage architecture. In stage 1, we cast a super broad net using hybrid search and RRF to grab the top 100 potential documents. Then in stage 2, we bring in a specialized AI called a cross-encoder for precision re-ranking. It deeply analyzes the semantic relationship between the user's query and those 100 documents, handpicking only the absolute best 5 to 10 chunks to actually feed to the language model.
Section 4. When retrieval fails, the conflict in the code.
All right, here is the plot twist of our story. Retrieval is definitely not perfect. Research actually shows a U-shaped accuracy curve when testing these models. This is known as the lost in the middle phenomenon. Turns out, if you shove way too many retrieved documents into an AI's context window, it remembers the info at the very beginning and the info at the very end, but it completely forgets the context buried right in the middle. It closely mirrors human psychology, specifically the serial position effect. If the answer is sandwiched in the middle of the prompt, the AI might hallucinate as if it never even read it.
And honestly, that is just one pitfall. We also see catastrophic failures from poor chunking. Think about it. If a really important idea spans 2 paragraphs and your system rigidly chops them into separate chunks, those related ideas get split apart and the semantic matching just breaks entirely. Other times, the system retrieves the exact right document but fails to rank it highly enough, or the AI just gets so overwhelmed by context noise that it fails to extract the answer staring it right in the face.
Section 5. The Enterprise AI Evolution, moving beyond chatbots. Because of these really high-stakes failures, businesses just cannot rely on basic setups. We can actually see how the architecture builds and evolves over time to survive real-world production. We started with naive RAG, which is that simple linear pipeline. But to solve the failure modes we just talked about, we evolved into advanced RAG, adding in pre-retrieval query rewriting and post-retrieval re-ranking. Today, enterprises are moving into modular RAG. This introduces complex, flexible routing that can decide on the fly whether to search a vector database, query a structured SQL database, or even search the live web.
So the absolutely crucial point here is this. For a business, truthfulness is something you have to intentionally engineer. Enterprise AI requires permission-aware retrieval. You really have to make sure the AI doesn't accidentally summarize an executive's private emails for a junior employee, right? It requires hard source citations so humans can cross-reference claims and rigorous human oversight for high-stakes decisions. It's a completely different game than just messing around with a consumer chatbot.
Section 6. Beyond traditional RAG, the agentic future.
We are now standing right on the edge of autonomous, multi-step retrieval. If we compare the paradigms side by side, it's wild to see how retrieval has morphed. From simple keyword lookups in naive RAG, to precision re-ranking in advanced, to the specialized tool integration of modular RAG. But the new frontier? That's agentic RAG. Here, retrieval is managed by autonomous agents that don't just pull data once, but actively plan, iterate, and refine their workflows completely dynamically. In an agentic workflow, the AI takes the wheel. With corrective RAG, the system actually retrieves a document, critiques its own retrieval for relevance, and if it decides the document is bad, it autonomously decides to go search the web instead. Adaptive RAG predicts how complex a query is before it even searches, routing it to the perfect strategy. And Graph RAG introduces multi-hop relational reasoning, basically connecting the dots across vast unstructured datasets.
Now, you might be wondering, modern models like Anthropic's Claude can now hold 100,000 tokens, which is dozens of pages of text in a single prompt. Doesn't that just kill the need for retrieval entirely? Actually, not at all. Even with massive context windows, chunked retrieval remains critically necessary. Stuffing 100,000 tokens into every single query causes massive latency, astronomical compute costs, and it triggers that lost-in-the-middle hallucination effect we saw earlier.
So retrieval augmented generation isn't going anywhere anytime soon. It's just getting smarter, which leaves us with a really fascinating thought to end on today. As AI memory continues to grow, and as these multi-agent systems become fully autonomous, will retrieval become entirely invisible to us as users? Or is it destined to become the very core of how artificial intelligence actually reasons about our world? Think about that. Thank you so much for joining me on this explainer, and keep exploring.